Hello and welcome to my CFD tutorial about electronics cooling. In this tutorial, we will make temperature analysis of Raspberry Pi 2 geometry, which is provided by the tutorial with these files. And in this tutorial, we will use simFlow. Actually, the graphical user interface for OpenFOAM. You can just download it from their website. Okay, let's take it to the other monitor and start the simFlow. First, it needs a case name. I'll just name it CFD Electronics. And create the case. I will just follow these steps one by one. First, it's empty, and we will fill it with the files that we downloaded. And here it is, our Raspberry Pi 2 board, CPU and pins. And next step, we will add a fan. Just rename it as fan, and these numbers are provided in the tutorial. I will just insert them and try to be as careful as I can be, because small things change big things. Okay, here is our fan, and we will add a fan inlet. For that, we will press geometry faces, and while holding control, I will press this face and create new face group and create group from 3D selection and rename it as inlets. Okay, for the outlet tool, I just create a box, name it as outlet tool, and enter the values in the tutorial. I'm gonna just check it. Okay. Here our outlet tool. Now we will enable board geometry meshing. We will just go to Hex meshing and RP2. We will press mesh geometry. We will make minimum 2 and maximum 3. And then we will just press the CPU. Minimum 2, maximum 4. And the fan. Minimum 1. Maximum 3. Oh no, not this. This needs to be 2, 4. Fan needs to be 1, 3. Yeah. Now we will go to the base tab and we will make these as in the tutorial. It looks okay. This will be 15, this is 10, and this will be 5. And that's it. this will be 1, and the X will be wall. Okay. Now we will go to the point tab, and the material points will be 0.055, 0.02, 5E04. Okay. And we will go to the mesh tab, and we just press mesh. And there's a warning, because we are using free license, we cannot mesh larger than 100,000 nodes, but below 100,000 nodes is enough for us in this case. We'll just say close, and it starts. And it meshed. Now we will convert solid to subregion. For that, we just press this and make subregion, and rename this region as solid, and press OK. And then go to the hex meshing and point tab. We will just make the material point like this for flutes, and go to the mesh again and press mesh, and the same warning again. We just press close, and it's meshing. And it's ready. Kinda ready. Now we will extract the outlet patch. We will go to mesh, we choose boundary, and extract from the outlet tool, and press extract. We will create a subregion called flute. Okay. Now we will press solid, we will choose these both with control button and create region interface, and they are linked. Now we just deal with the remaining parts. For this case, boundaries will be wall, fan will be wall, fan inlet will be patch, outlet will be patch, and Raspberry Pi 2 in flute will be wall, and Raspberry Pi 2 in solid will be wall also. And we will set up the solver. We will go to the setup, we will choose multi-region simFlow and press select, and all new things appeared here. Now we will set up the radiation, but first we will not use the radiation, but we just setting them up for future. Radiation, we will disable the radiation for now, and the radiation model will be surface to surface. Maximum brace will be 3 million. Now we just go to the thermo tab for thermophysical properties. We will choose solid, and from material database we will choose aluminium and hit apply. And for the flute, we will just flute. From material database we will choose air and hit apply. Before going out from here, we just equation of state incompressible perfect gas. And after that we will go to the turbulence panel. For turbulence modeling we will use runs, the key epsilon model we will use, and we go to the solvers from solution. We'll just choose H solid and open this sub bracket, and we'll just change them. Relative tolerance will be 1E02. This will be 100. This will be the IC. Okay. Now we will go to the simple. Orthogonal characters will be 2. This will be stay 1. Go to the relaxation, and we will just fill them. (0.8). Yeah. Now we will go to the limit step, and raw max will be 2. My hotkeys are working when I press the numpad. Sorry for that. And we will enable temperature limits. Those will be 2290 and 600. Now we will go to the cell zones. All cells in solid source term. H will be 100, 125. I think there's 4 zeros. 1, 2, 3, 4. This will be remained 0. Now we will go to the boundary conditions setup, and we will change boundary condition for outlet to pressure outlet. This is our outlet. We will make it to pressure outlet. We will go to the turbulence step. We will make the K type 0 gradient and the epsilon type 0 gradient. Okay, we are ready to run the simulation. Here, the end time represents the iteration number. For this part, we will use 800 and run the simulation. Right now the process is around 780 and it's near to end, and calculation finished. It's okay, and you will go to the post-processing, and there's a built-in post-processing software in simFlow called ParaView. We will just use it. Run ParaView. We can make it like this without blocking the camera. Okay. Right now we will just go to the last frame, which is the last iteration, 800, and hit apply. Now this is our board, but it's blocked by some fluids or like this. We will just hide them. We will just press mesh regions and deactivate the fluid, internal mesh and fluid boundaries, and hit apply again, and there's just our board and the CPU. Right now it looks kinda make no sense. For that we need to change the P to T. Right now it's temperature, and we will rescale to data range, and here it is, our display temperature. Okay, we can just close it. Right now we will enable the radiation. For that we will go to the radiation panel and hit enable radiation, and solution frequency will be 5. Now we will go again, run the simulation, but this time with 2000 situations. Now I just wanna show you the performance numbers of these application like this. Right now my CPU is running around 15 to 18% utilization because I am recording this with OBS, and there's YouTube and just other Mozilla Firefox pages, and it's around like this. When I hit run, we will just see what it will increase and how much this program consumes processing power. And solver starts to run. When it starts to iterate, I will show you again the performance, and we can just compare. Yeah, it started, and we can see the utilization is right now 36, 37, 34. It's around like in this area, in this margin. We can see just 20% increase, so it's not that much. So you don't need a high-end CPU like this for running this program, but for high-end CPUs like this, I just think this program needs a high demanding processing power mode to just decrease the time consuming with these iterations. Right now we are around 1980, and it finished. Now we will go again to post-processing with ParaView, and again we will go to the last time, hit apply, and again just deactivate the fluid, internal mesh and boundaries, and hit apply again, and it's like this. Again we will just change it to T and make sets range, maximum will be 2362, and press rescale, and it becomes like this. It's not red like the other time because with radiation this CPU cannot reach that temperature level because it's radiate the heat, there is convection, and I think it's below 346 kinda, but the last time it was 362, like in that region. In this scenario, radiation plays an important role because this CPU now did not reach that level of temperature. For this importance, we need to show the radiative heat flux also. For that, we just make it to QR partial and uncheck the solid internal mesh and solid RP2 CPU and hit apply, and now we can see the radiative heat flux around the board, excluding the CPU. And it's the electronics cooling simulation with CFD software simFlow. Thank you for watching.